So hello everyone. So welcome to our this week Progress in Vision AI seminar talk. And today we're glad we have the Professor Jie Gu from the Northwestern University to give this talk. And Professor Gu is currently associate professor in Northwestern University in the ECS department. He received his bachelor degree from the Tsinghua University, master degree from the Texas A&M, and a PhD from the University of Minnesota. From 2008 to 2010, he was with the Texas Instrument Dallas on research and development of ultra low voltage mobile processors for smartphones. From the 2011 to 2014, he was with MaxLinear, leading developments of the home multimedia broadband SoC chips. He joined the ECE department of the Northwestern University from the 2015, working on novel circuit and architecture for low power microprocessors and machine learning accelerators. He received the NSF Career Award. And now let's welcome Professor Gu to give this talk, Boosting Deep Learning Accelerator with General Purpose Computing and Cognitive Reasoning.
Okay. All right, so thank you very much, Bo, and thank you everyone for coming to this talk. It's really my pleasure to come here and introduce some very recent work we did in our group. I assume you can see the screen and hear me well. Let me know if there's some issues. Let me move. Okay, so this is the outline of today's work. I'm going to introduce something I think very special that we did in our group, which is I'm going to first talk about the motivation why we do that, but we are trying to introduce something different from the conventional Van Neumann or deep learning architecture. We are trying to build something in between. So to give the example how we do it and what's the benefit, I'm going to show two architectures we derived. One is referred as neural CPU, and based on name, you can already see this kind of sort of like a unified architecture. Another one is called a differentiable neural computer for cognitive reasoning. These two are for a little bit different applications, but in terms of architecture, there are similarity. So at the end, I think I'll conclude with some of insight that we think there's interesting opportunities in developing new architectures these days. Before I get to my talk, I just want to quickly introduce our group and our school. I hope some of you have a chance to visit us. So we are in Northwestern University. We're actually in a pretty nice location in Chicago. We are about 40 minutes away from downtown Chicago. So we are in a pretty quiet suburb neighborhood, but we can actually see downtown. So you can see this is Chicago downtown, and we are at the north side next to the Lake Michigan, and we can actually overlook the downtown skyline. So we have pretty nice campus here. So welcome to come to us and contact me if you have a chance to visit Chicago. Here, I just give a quick overview of what do we do in our group. We are a circuit group, so we do really pretty low-level circuit design, but we expand in cross-layer development. So we started from circuit, and we built something special using non-conventional circuit techniques. For example, mixed-signal computing technique to improve certain amount of computing tasks, including complicated computing tasks or the deep learning tasks. And you can see at circuit level, we do a mixed-signal computing, we do computing memory. At architecture level, we develop some things special for us and compete with conventional CPU, GPU, or CNN accelerator. And that will be the focus of today's talk. And we leverage our expertise in the chip design in our group, that we also build a wearable system. So we assemble the chips together with components and build a AI-empowered human-machine interface. So there are our chip, including both sensing and also AI function in it to help human for their daily operations. So that's you can see we do pretty broad development in our group. And here highlighted some of the work we do. At circuit level, I mentioned that we do something quite special we call time domain, which is kind of, there's similarity to the spiking operation, but it's not really just spiking. We encode the information into the entire length of the pulse. And we use that to solve some problem, like a dynamic problem, dynamic programming problem. And we build a computing memory design also, which is a very popular topic in the circuit domain these days. But in today's work, I will highlight two of our work in building novel architectures for AI and domain-specific computing. One is the neural network-based general purpose computing. The other one is the differentiable neural computer for logic reasoning. And these two actually have very similar ideas behind that. So I put them together, and both of them are very recently published. And at system level, I already mentioned that we built some human-machine interface chips. We're a chip group, so I think chip group would like to show off some of the chips that we built. I look back into the past 3 years, it turns out we built a lot of chips. Some of the chips are doing the biomedical signal processing, as I said, for human-machine interface. Some of them are using mixed computing to solve computing problem. Some of them actually are processors. We build GPU, CPU as well. Recently we built more of deep learning accelerators for accelerating deep learning operation, but using, as I mentioned, analog or mixed signal kind of approach. We also recently built a 3D, 4D point cloud sparse convolution neural network, which is kind of interesting. We just published this year. But in today's talk, I'll focus on 3 chips we built along the line of what we refer to as neural CPU, which is kind of a very special architecture we built in our group. So I'll talk about these 2 works. With that, I'll jump into more technical discussion now. So as a motivation why we do this work, here we show, I think now it's a widely accepted knowledge that the conventional embedded processor now really have had a hard time to solve the current AI or domain-specific computing jobs. Here we show that the top 12 mostly used, widely used embedded processor. If you use it to do even a single image inference using VGG16 model, this is the computer time. It takes 10 to 100 seconds, even more, to finish, and definitely it has hard time to meet a real-time target. This is the computing bottleneck, and then in terms of cache or memory bottleneck is even more. The processor require 100 to 1,000 times loading because of the limited memory access, and at the end you will be bottlenecked by the memory access. So this comes back to say that the conventional architecture have a major trouble to deal with the computing workload that we are developing these days, and especially that's for the von Neumann architecture. To deal with this problem, there has been really a boom of development on the accelerators, and this is left is the survey performed by Tsinghua University. They collected all the published accelerators for deep learning operations, and on the diagonal direction, that's the higher efficiency. So you can see we started from CPU, and then there are a lot of development of FPGA and the GPU. Of course, the ASIC would do better because it is specially designed. And even within ASIC, there's a conventional digital ASIC and also mixed signal ASIC, which actually this is a yellow dot. So you can see that we are more and more developing ASIC to deal with this kind of AI computing. And on the right side is the survey from Deloitte that is showing the growth of the AI market, and especially for the edge chip, where we put the AI computing capability function into the small chip, into our wearable device. And we are right now in the middle of a really fast growing in this market of edge AI chipset. Okay, so what are the challenges? Here I highlighted some challenges, and this is especially for end-to-end operation or end-to-end real-time operation. The conventional architecture is what we call, we refer here as a heterogeneous architecture. We have a CPU and also a neural network accelerator. So these two communicate through a DMA managed bus. And so the data has to travel across them. For real-time application, the issue will be, a lot of issue will be the latency. I'm showing you on the right-hand side is one of our, we have some collaboration with the Ryan Shirley Ability Lab or the formal rehab center of Chicago. For them, what they need to do is they collect a large number of sensors from humans' muscle, and they have to perform a deep learning type of classification on the muscle signal to derive people's intentional movement and use that information to control the robotic arm or legs they have. You can imagine that all this operation with so many channels, classification has to be done within 5 millisecond time. This poses a lot of challenging for computing requirement. So the latency is actually very important for real-time application. And we have been always fighting for efficiency, which is TL per watts, but that doesn't reflect all the requirement. The end-to-end system latency and performance is very, very important. And in terms of end-to-end performance, actually the general purpose CPU operation, in fact, dominate a lot of real-time applications. On the left side is the very recent published paper from Meta. So they build, as we all know, they build the VR AR chips for their VR goggle, right? So for the gaming purpose. So for those, they give a pretty detailed operation sequence of their VR applications. And here I just grabbed the one piece of that, showing in one of the CNN layers. So they have a CNN accelerators, they have CPU, they have memory management, and this is, I think it's in 7 nanometer technology. So they fabricated the chip and published this chip. And if you look at the detailed description, you realize that the CNN operation is only take a very small piece of the whole end-to-end operation for this AR image processing. Essentially, I have to finish it in time to allow user to use in this virtual reality environment, right? So the CNN only takes small time. There's a huge amount of effort have to be done by CPU and also data movement, which is again controlled by the CPU. So this is, you can see that the pie chart of the operation. Similarly, Intel have published IoT device. Again, it has a CNN accelerator in it, but they show the whole operation sequence. It's basically they're trying to take a picture of the insect that captured and classify what kind of insect it is. And again, CNN only take a small portion of the entire operation, and then the CPU, the image processing, the filtering, sensor operation actually dominated the whole operation. So this come back to say that if you consider the real-time application, the CPU cannot be ignored. And but that doesn't mean actually CNN is now useful. If both of these chips have CNN accelerator in it, if you eliminate that, then of course the CNN gonna become a bottleneck. But nowadays with the accelerators on the side, then we have to look into the entire overall performance of our job. And this challenge will be similar as what we mentioned, but it's from the accelerator side. We see the accelerator are very highly underutilized. Here is showing the published work we gathered before, including even the TPU from ISCA. The accelerator actually all of them are showing between 20 to 35% of utilization, where entire operation are still dominated by CPU and data transfer. And the reason for that is because the CPU are so heavily used, a lot of time accelerators are actually being idle and waiting for the data to be prepared and come back in. This is especially for real-time usage, because if you are purely just doing inference, you could pipeline the operation or doing multi-batch of image, which could somehow hide this latency. But for real-time usage, you can't hide it. You have to go through the sequence. So that's one of the problems. In addition, there's the third issue, which is actually I will talk more when I talk to the second half of this seminar. It's the CNN model right now have two limitations. One is the support for external memory, for very large scale memory. Another one is for building up the relationship for logic reasoning. So this is actually inspired to another architecture I'll talk about called differentiable neural computer, which is better in terms of building up a sequence reasoning task. So with that, I'll come down to our idea of improving our AI task. So fundamentally, we know that there's this is extreme cases of von Neumann architecture and the deep learning architecture. The von Neumann architecture is poor in terms of the efficiency. This is because we already know that this pipeline overhead we are paying. We only need 6% of effort, only deliver 6% effort, but we are paying such a large overhead for establishing the pipeline operation, grab data, and save back the data. So that's the problem of the von Neumann architecture. On the other hand, the deep learning architecture are much more efficient, but it's not flexible. It doesn't support all this general purpose computing job that we need. In addition, the deep learning have trouble or have limitation compared to von Neumann architecture for the memory access. So with that, this inspired us to come with a different direction of development. So we know that deep neural network-based computing has become very popular, or potentially become a common computing platform for the future, right? If you read those machine learning conferences, we pretty much can use that to do majority of the work nowadays based on the deep learning architecture. But we have a problem of the programmability and the large memory access. So what our idea is, can we develop, try to reconcile the difference between these two vastly different architecture and develop something in between, or we refer to as a unified architecture that incorporating both DNN and CN. So we know if we start from CPU and I mean DNN and CPU. So if we start from CPU and then incorporate DNN into it, we know it's not very efficient. So we decided to start from DNN accelerator, which represents the most efficient architecture for deep learning. And then we added the general purpose support into it, so that we can have one architecture that can support both purposes. And this kind of resonated from the bigger picture point of view to the current development of software 2.0 and 3.0, where the programming tasks, or even general purpose operation tasks are converted into deep learning architecture. In the past, though, what we had was the human being have to engineer the logic and write the code and let the computer to generate output using CPU. But nowadays, we could potentially give a data set and define our desired behavior and train the deep neural network, and it could generate the output behavior. This will take people out of the loop of the operation. And actually, in the second half of the talk, the idea of logic reasoning also follow similar kind of motivation in here. Okay, so there's actually one interesting work I want to mention before we jump into our architecture. This is a published work from Google on building what is called neural ALU. As we know, ALU is the central piece of the CPU, which you can use to perform many different type of logic, Boolean, or arithmetic operations. So they modify the neural network and try to train the neural network to perform ALU job. So they show that they can do it in a pretty nice way. The accuracy pretty high. So we did that exercise in our group as well. And what we realized is that if you start to train the deep neural network to do the ALU job, it can do a single job pretty well. But if you train with multiple jobs, which is needed for the CPU, I have trouble. Hello? Okay, I'll continue. And also, once you combine the arithmetic operation with some Boolean operation, the error actually increased. We found a way we can train better and can improve the error. But once we convert it into hardware, this is a comparison with the neural ALU and the conventional ALU. You can see the size also are pretty big. So that means it's not very efficient to do if you directly use a neural network to perform this kind of CPU job. However, the direction is attractive. It leads to a potential unified architecture for solving majority of our computing problem. And that's the motivation for us. So now let's jump into what we are doing here. We call it the neural CPU. It combined deep learning and van Neumann architecture. Okay, so I think it's not difficult to imagine what we do here. And here at the high level, at the higher level, how it looks like. So rather than going through the conventional heterogeneous two-core operation, the two-core configuration with CPU and also accelerator, we combine them into one core. And this core is really deep learning based. However, we use the individual neurons in this in existing accelerator to recover the pipeline operation of the CPU, so that even the same CPU the program can be executed inside this core. The benefit is, first of all, it's a one core system, so we can demonstrate we have less area and cost. And also the benefit is we have lower latency due to fully utilizing of the computing unit. So our utilization reached more than 90% compared to the heterogeneous case where there's a lot of idle time for the accelerator. And also we remove the data movement because data doesn't have to travel across the cores. Our data all stay within its own cache and never move out of it. So along this idea, we implemented two versions of the operation. One is the binary neural network based. This is an earlier version. And then we have a newer version, which is really just using a most popularly used Caesar array based accelerator to embed CPU operation. And we have both of them have test chip to demonstrate our architecture. Okay, so I take this a simpler example first to talk about how to reconfigure binary neural network into a RISC-V. So from high level point of view, this architecture, it actually looks similar as our RISC-V pipeline, where we have a 5-stage pipeline, 32-bit instruction, and also a register file. And RISC-V, we are using the RISC-V RV32i instruction set. We try to reuse the neurons, and the neuron you can see that we have XOR and adder and register inside the neuron, but there are a lot of neurons. So we reconfigure the neurons at each layer to perform the pipeline operation of the RISC-V. So we started from a very basic 4-layer neural network with 100 binary neurons at each layer, because this looks very similar to the CPU architecture. And we built this neural CPU data path by reconfiguring the neurons into pipeline stages. For example, the program counter stage, instruction fetch stage. So we, for example, in the PC stage, we reuse the adders and realizing counter to allow the branch operation and the PC operation in it. The decoder stage actually is the easiest one to reconfigure because the neural network essentially is a decoder. So we can almost pretty much use the same logic to realize the decoding operation and decode the instruction into the opcode that needed to control the ALU. In the execution stage, besides the adders, which can be used for all the arithmetic operation, we have to add some Boolean operation support, but the overhead is very small because the Boolean operation is very easy to do. And there's a memory write back and a register file write back stage. Those are mainly we just reuse the register files in it. Also, we reconfigure all the memories. So the memory that all have a dual purpose, either as input await memory in the neural network mode, or the memory are configured into the CPU mode as a data cache. So the key idea is the data, once you finish in either CNN mode or CPU mode, when you switch into the other mode, the data stay in it and doesn't have to move around the different cores, which brings the majority of the benefit we see in our architecture. So we built a test chip using TSMC 65 nanometer technology, as shown in here. We built 2 cores so we can configure them into CPU plus accelerator to make an apple-to-apple comparison with the conventional approach. We verified it in our lab, performing the measurement and also measure the power efficiency. So first of all, if you only use a single core to realizing the 2-core function, we can achieve 35% area saving. Each core here have very little overhead, so you're as efficient as the either accelerator or the CPU. So, so this is important because you don't want to add more overhead for each separate job in here. Now, if you compare with a dual core architecture, because our CPUs can be fully utilized, we don't have idle time in as a conventional case. We also don't have the data traffic that need to be sent across because they're independent and each of them can perform DNN and also the CPU job. We show we can improve the end-to-end performance by 43%. And those are some measurement operation of the power and the efficiency. We use the real-time image classification and also gesture classification case to test this chip. Okay, so at this point, actually, that's our first version of test chip. We published in Micro 2020 and got a lot of attention. In fact, Samsung invited me to give a talk to their Samsung forum and also meet with their neural processor team. So we chat about it. And the obvious questions I received was the binary neural network is not that useful. I mean, from the industry point of view. So can we do it for a more commonly used CNN accelerator? If you look at this architecture, you find out these two are very, very different. The CPU and the accelerator are very different. But we take the challenge, we tried it. So our idea is the accelerator much bigger, but we could also scale up our CPU. So what we end up doing is we take the original systolic array-based CNN accelerator, and we recover multi-core CPU out of it. Because we have so much PEs to use, we recover into 10 different RISC-V CPU cores. So essentially, one accelerator can become, one accelerator can become 10 core RISC-V CPU. And that's what is showing here. In one, we call it systolic neural CPU, we can either become a 10 by 10 systolic array for CNN operation, or we can configure into a 10 core RISC-V CPU. And again, we support all the RISC-V instruction set. So your RISC-V programs from your REFAI compiler can be directly downloaded into our CPU and be processed. How to do the configuration, I will not get into detail again because the idea is similar to our binary, but binary neural network, but it's much more complicated. So we were able to reconfigure the 10 by 10 Accelerators array into 10 CPU cores. Of course, each PE has to be customized, in fact, into certain groups of the operation. And in terms of overhead, there's about 10% area overhead and 15% power overhead by adding this additional logic into that. But we have a pretty significant improvement, so I think it can justify the overhead we're paying. We have a very special data flow in this case. The reason is, as I mentioned, our goal is to remove the data movement. So when we switch the mode between CPU and CNN mode, we don't want the data to move at all. And the whole operating system, we're targeting the end-to-end performance operation, which means we need to use the CPU to do the pre-processing, which include the image reshaping, resizing, grayscale, rotation, normalization, or data alignment. Then you pipe into the DNN mode to perform the first layer operation, and then come back to CPU to do, again, data post-processing, padding, alignment, and come back to the another layer of DNN. So this is a whole sequence. The challenge now we see is, yeah, our idea is we want to keep the data local and also no movement. But if you look at the systolic array operation, naturally the data actually are moved to the other side. So for example, if we start from the CPU where the data are grabbed from data cache, after you finish, the data is still there. But once you move into CNN mode, the data are launched horizontally and finish vertically into output memory. So now the data actually at a different side. Then the CPU have to grab data from another location and then send back. So to deal with that, we have this rotationary data flow where we're configuring our CPU in two different modes. One is a row CPU mode and column CPU mode. Similar to our accelerator, we have two different data flow support. By doing that, at each time when the data finished, the next operation will directly take the data and then fetch it. So there's no data movement. So by doing that, we will eliminate the data movement requirement. And here showing the conventional case where the CPU are doing processing and data transfer, and the DNN may be waiting and finish and then come back to CPU. In our case, they're fully utilized. The data transfer are eliminated, and also our CPU are much faster because we have 10-core CPU now due to the the computing resource that we have in the systolic array. So that's where the benefit comes from. So to demonstrate that, again, we built a test chip in 65 nanometer. The total area is about 7 millimeters square, and we can achieve. We measure the power efficiency. In terms of CNN efficiency, we have about 600 kiloops per watt. It's not the best in 65 nanometer, but it's on par with many published other test chip work. We also measure the utilization and the power operation. We can achieve more than 90% utilization in this chip. Here is a apple-to-apple comparison with conventional architecture. We use a Gem Mini because that's open source. It's very hard to find other commercial accelerator. How do they do exactly end-to-end performance? So we compare with Gem Mini with this architecture. So we compile the same work, and because it's also REFAI based, we can use the same compiler and generate our work and do the end-to-end performance for image processing in here. We show in most of the cases we have 60% or more benefit in terms of speed up. Only when the data set becomes too small that when you require very less CPU involvement, then the benefit go down to 40%. And more importantly, the inter-core data movement has been eliminated, which actually also lead to a lot of power saving and also the performance saving. Okay, at this point, let me see how I'm doing. Yeah, at this point, I want to jump into another architecture, which is we call it the differentiable neural computer for cognitive reasoning. It's a different application, but once I get into it, you will realize it actually share quite a similarity to the neural CPU concept, because essentially we are trying to borrow the benefit or the architecture feature of the CPU to improve the deep learning operation. So let me get into that discussion here. We all know that deep learning can do a pretty good job for image classification, for the natural language processing job, but the human beings are doing some job that's even more complicated than that. And this is especially for the reasoning task, where we can handle or develop a working sequence to deal with complicated workload. That is hard to be done using just our existing deep learning approach for classification. So the example of this kind of commonly used human logic reasoning task as showing on here. For example, the deductive reasoning, where you give a existing pattern of the signals or images, you want ask people to realize what's missing or what's the next of that. Or the context sequential reasoning task. This is the one I want to just spell out, because this help us to understand what kind of reasoning task I'm dealing with here. This is you are given a sequence of sentences, and this sentence can go as long as 10, 20 sentences. And you're asking question that based on the information from the sentence, but the question is tricky. So for example, in this case, Mary took the milk, and then John moved to the bedroom, and John is now related to the previous sentence. So there's noises in the next two sentences. And then Mary traveled to hallway. The question is, where's the milk, right? So you can see that you have to kind of build up a relationship between Mary and the milk, and then Mary and the hallway, then you know the milk sort of in the hallway. So this kind of logical reasoning is not just simply understanding the sentence. It's also require we to be intelligent in figuring out the relationship. And that's one of the tasks that human beings are performing. And similarly, there's this networking task where you give a relationship of two persons, then you try to derive the family tree of the two family members. And a lot of derivation algorithms are also fall into this kind of a reasoning task. For example, sorting. How do you sort the numbers? And also there are a lot of map-related image processing in it, how to traverse a map to reach a destination within certain steps. Those are typical jobs that human beings are performing, but very, very challenging job for the computer. Conventionally, we use either exhaustive search or more of a very handcrafted, sophisticated heuristic search algorithm to deal with each of the problems. But these days, there are more interested of using deep learning approach. The benefit of using deep learning approach for this kind of reasoning task is it's trainable. Because neural network is differentiable, so you can train it with given data set, and you don't have to rely on human being to derive very sophisticated algorithm to do that. So deal with this problem, there's one type of brain-inspired computing model. That's what this work will follow. So the neuroscientists have been working on this for 50, 60 years in coming up with a computing model that human being for use to do the logical reasoning problem job. And it turns out there's an established consensus that the human human brain uses something called a working memory scheme, where this is a short-term memory compared to a long-term memory, which is another portion of the brain. The short-term memory compare and work with a central controller, which is called the central executive. Together, used to realize this kind of more complicated sequential job in human brain. And people over the years, this is still under developing. The neuroscientists are doing a lot of small experiments to understand the working principle of the working memory. And but we already know that a certain portion of our brain are performing certain portion of the job as shown here. For example, the central controller are done by the prefrontal cortex, and also the verbal memory and the visual spatial memory are kept at different regions of the brain. What's interesting is if you look at this architecture of human brain, it's actually quite more complicated than the CNN architecture that is mainly used for the visual cortex portion, but not for the deeper logic reasoning. And also what's interesting, special to us who work on architecture, we see that there's a strong similarity between the working memory principle and the von Neumann CPU, where we have central controller and control a short-term memory, which is cache. So this is kind of opposite of what we always try to do, that we try to build a CNN type of computing platform, which allow us to do more complicated cognitive job. But in fact, if you look at this architecture, we see that the CPU or the von Neumann architecture have its own merit in terms of dealing with the more complicated tasks. Especially the benefit is one is the cache or memory access. Another one is building up the relationship for logic reasoning. But keep in mind, all these are neural-based. That means the detailed operation is not the same as the CPU, where you simply just write the address and read the address. There's still a neural network-based operation, which means this is also differentiable. It can be trained. So based on this brain-inspired architecture, people come up with this architecture called the differentiable neural computer. This actually was initially published by Google into Nature 2016, and then followed by a very large number of subsequent works using this principle to deal with a different type of task. So here I'm showing it at the high level how this DNC model look like. It has a LSTM, which used to control the input sequence, because remember you have an input of sentences. They try to derive the sequence of the input, and then send the input values into a very specially built, they call it attention-based memory controller, which break into a read head and write head. So these two heads are used to direct the input information into the memory, which is the external memory. So that's where all our knowledge are saved. But they use this attention-based memory controller to redirect the memory or retrieve memory from the main memory. And this controller is neural network based, so it can be trained. So from high level point of view, it actually looks quite similar to our von Neumann CPU. But this is the attention-based memory is the very unique part of this operation. So here is some mathematical model of this DNC. I will not get into too much details. You can refer to the original Google paper on it. But I want to highlight some very special computing effort in this model. First of all, is this memory controller that's special, and they call it the read head and write head, which is just like our CPU or our computer. And also, there's a very special setup in this controller, which they call it the linkage memory or attention memory for the read. This special memory are used to set up the relationship between the main, among the memory content in the main memory. So essentially, there's small memory in here, keeping track of the logical relationship of the memory content in the main memory. And this is the central piece that allow us to do the reasoning task, because we know who and who are related. And beyond that, for each operation, there's this cosine similarity calculation, which are basically search the memory for the similarity between the input pattern. This help the computer to redirect the focus to the relevant memory portion. So combining this similarity calculation and also the attention-based retrieve of the memory content, they generate the weight that they use to read out or write into the main memory. In the right side, there's also a special memory called usage memory, which is used to track what memory has been used or most memory have not been used. And combining with, again, the similarity calculation is used to write a certain portion of the memory. So there's a dedicated location to write the memory. So in summary, you can see there's this unique operation with similarity calculation, the usage tracking, the attention calculation, and also the memory are write in a neural network way, so which is a soft max operation into the memory. So this whole operation is differentiable. So the benefit of that is it's trainable. So essentially, you don't have to ask human being to come up with the algorithm. You can give the data set and give the expected behavior and then train this network so that you come up with a solution by itself. That's one of the major benefits of this model. So compared to the existing deep learning model, here's a quick benefit of that. CNN, of course, we know that have trouble to deal with a sequential operation where in the logic reasoning, we really need a sequential operation capability. So, so the LSTM actually are more closer to the DNC model. However, we know that the LSTM have quite limited access to the memory, which is one of the major issues of LSTM. But in the DNC model, you can see the memory actually are separated from the computing element, so that the memory can be extended to very large. This is one of the major benefits of the DNC model. And also the memory are now mingled together with the computing element, which provide more flexibility. And this is why when doing the reasoning task, the DNC actually are showing much better performance in terms of accuracy than the LSTM. So to us, as a more of a hardware group, we're interested in, can we implement this kind of task or this complicated computing model in a small chip so that maybe in the future our cell phone can do this kind of reasoning task, right? So we started this operation and come up with the architecture solution. So what do we firstly see is there's a very different, the operation is very different from CNN. So the conventional CNN architecture won't work in this case. One is there's a huge number of memory access for the even same memory content. You have 200 times more access to the memory. And also there's a memory bandwidth limit in here, that the bandwidth requirement is 10 times larger than CNN. This means the conventional C-solid array will have major trouble, and that leads us to our architecture, which is near memory architecture. And we also leverage the sparsity and data compression technique to improve the efficiency. So from high level point of view, this is what we had on the right side. This is what we had in terms of the computing architecture for this particular model. On the left side is a conventional C-solid array-based CNN operation, where the problem, if you look at the map into this model, is that each PE has to access a large number of different memories. And especially if you scale up the PE array, you have the data has to travel very long distance across the entire array, which causes a major congestion of the traffic. This is the C-solid array is not suitable for this architecture. Instead, the nearest memory kind of architecture is much better, because now you can break the memory into smaller distributed memory in this case, and the computing units are much closer into each memory, so that the data traffic will be much easier to handle. And then we can scale up each tile, which contain both computing and memory, into a bigger portion, into large number of tiles. And fortunately, most of the data are local, so only small amount of data have to travel across the bus into different tiles. And using this architecture, we can significantly extend the memory bandwidth, and also the architecture is much more scalable compared to the C-solid array. So that's the architecture we use for this implementation. This is a more detailed architecture. I will not get into the details of it. I'll go a little bit quicker now. I think a lot of them are implementation details that when you start to work on it, you can refer to our paper. So, but you can see that the memory now are distributed into the tiles, and there's also computing support, very specialized computing support inside each tile. The operation sequence is actually very complicated. For each iteration, there will be LSTM and then special write weight generation, erase weight, attention calculation, read weight, rate, and fully connected layer. So they're not simply just a neural network operation. And this 5 stages operation has to be going through 500 iterations until the one inference job can be done. So to do that, if you simply just write ASIC, it won't work because your majority of your ASIC will be idle. So we have to build a reconfigure logic that allow us to use a similar PE to perform all different type of jobs in here, so that our utilization, again, you can see here, are higher than 90% on average. The data flow also need to be reconfigured because for different calculations, such as the cosine similarity or the transposition, the data flow are different. So it's very important to have a reconfiguration in the data flow inside the PE. And the PE also are reconfigured in supporting the similarity calculation, the dot multiplication, subtraction operation, and even the precision we build have a mix of 8-bit and 16-bit. Because for neural network operation, we found out we can do 8-bit, but for memory operation, we have to go with 16-bit. Otherwise, the accuracy will drop a lot. So at the end, we quantize the operation, and we have 4% loss in terms of the accuracy compared to the floating point operation. I'll skip those few slides on how do we do the zero skipping and sparsity, because some of the effort actually have been also used in other CNN type of accelerator. We also did the data pruning on the chip to eliminate the redundant data so that our processing will be more efficient. Okay, so I jumped into the final result in here. We built fabricated test chip in TSMC 65 nanometer again, and it's a 7mm square size of the chip. Here I'm showing some detailed insight of how the chip will behave, which is interesting. Although the task looks relatively simple, but actually this kind of task people use to test cognitive function of the human being. They ask people to repeat input pattern, for example, input the phone number or digits, and ask this person, especially the person who suffer from brain damage, to repeat that and evaluate their cognitive function. In this case, the computer get the input pattern and expect it to generate the output pattern. Well, this sounds an easy job, but if you imagine a computer have no idea what to do and you don't allow a human being to program it, then how would that figure out what to do? So after training, it will form its own algorithm to do it. So as I'm showing here, once you take this example, you have input and the data are being read into random addresses, but the computer, as I mentioned, have this attention memory, which will keep track of the relationship of the random data set. And this white dot representing there's a data relationship between this, let's say 5, data point 5 versus data point 3. So it kind of will keep tracking of the certain pattern or relationship with the data input. And once you retrieve it, it can generate the output. And similar tasks we tried on the sorting operation, which is more complicated. We found out that the computer sort of after training can figure out the algorithm that's very similar to our human-derived algorithm to perform the sorting job, which is very interesting in terms of this computing method. And again, this is differentiable, so it can be trained. Similar tasks can be done by a family tree task where you give the relationship of the family members, and then you ask computer, what's the relationship between David and Amy, which is a maternal great uncle relationship. The computer will build up this relationship map using attention memory and come up with the solution. So, so we show the accuracy in the measurement and also the performance of this work. Similarly, the context, the question answer problem I mentioned before was able to be performed in this computer. And then the underground map traverse where you give a starting point and end point and tell computer come up with a route for me within 7 steps. So it will come up with a solution like that. Overall, so these are the measurement data from our test chip. We measure the power. The power actually are very different in different stage. The LSTM and the fully connected layer, basically the neural network still dominate the whole operation. And the efficiency we get is about 300 TL per watt, not that high, but also not too bad in terms of this efficiency. And we tested in 8 different reasoning tests: the copy, repeat, sorting job, context Q&A, family tree, traversal, 40 pass. They generally have a 3 to 4% loss of accuracy compared to floating point operation, but we have very significant improvement over CPU and the GPU using this test chip. All right, I think that's what I have all. I just want to give a quick summary. So as I mentioned, we're trying to explore some new architecture in this work. So we know that there's a trade-off between the von Neumann architecture and the deep learning architecture. So in this work, we try to do something in between, which develop a general architecture which can support the general programming, also can reduce the intercore data movement. And we should be the neural network based because we think neural network in the future could be a common platform. It's very efficient for deep learning and also trainable. This is one of the major requirements for building the future AI. And we showed 2 architectures in this talk. One is our proposed neural CPU, where we recover the REFAI operation inside the C-solid array, and we can show an improvement of 65% due to reducing the data movement and accelerating the CPU job. We also show, following similar concept, if our deep learning can adopt some CPU-based access to the memory, we can use it to perform reasoning tasks. And we build the hardware acceleration for the differentiable neural computer architecture. And we show that we can perform many different reasoning tasks with significant improvement over the software solution. So with that, I'll conclude the talk, and I want to give an acknowledgement to our funding agency, NSF, DARPA, and SRC. And thank you very much. I'm available after the talk, so I can stay here longer if you have questions. And yeah, thank you very much.
Thank you, Jie. So very, very interesting talk. Questions from the audience?
Hello, Professor. Yeah, hello, Professor. My name is Ling Yi, and I'm a PhD student from Rutgers. Very amazing talk. I'm sure I learned a lot from here, and especially for the neural CPU work. And I'm sure it's very interesting, and I learned a lot. So basically, I think it's just it's a combination of a general purpose processor with like a convolutional neural network based accelerator. So we can combine them into one core. So my question is, as we already have the neural CPU, we can do both the general purpose calculation and the CNN based calculation. I think people will now expect some more, since we know we have RN, we have GN, more and more things. They may expect whether we can have a CPU and a combination with a GN accelerator, RN accelerator. Do you think it's will be very challenging to do that? Or maybe in the future we can have a CPU based with another general neural network based accelerator, like we can support different neural network algorithm on chip?
That's a very good question. If I give a quick answer, I don't think there's really a major challenge in doing that. Or what we start with is the convolution is a CNN accelerator, which is most commonly used. There's nothing really special tell us we have to use the CNN and not using RN or fully connected kind of accelerator. the architecture of those cases are pretty similar. So I don't think there's a major issue. The only thing is, even for the deep learning accelerator, if you try to deal with multiple type of neural network, you may start to lose your efficiency, right? So if you want to deal with the fully connected layer and together with the convolution layer, you may have to add more data flow support. So, but those are common. Those are needed for supporting different data flow. So for configuring into our architecture, on top of my head, I don't really see any major challenges there.
Okay. Thanks for your answer.
Thank you.
I think there's one question from the chat box.
Mm.
Can you see that?
Oh yeah, I see that. Well, we have someone from I think Nanyang University, right? Or so is it possible for one core to act as a CPU all the time to access some interrupt flag that need to be handled timely? Yes, it is actually. When we build it, we add much more function that we think we may need. Let me go back to our neural CPU job in here. Go back. Okay, so go back. In here, actually, we didn't show in our paper. When we build it, sorry, somehow there's a lag in. Yeah. So in our, the question is, can we not just fully utilizing all the to configure all the PE into all the CPU or all the CNN? Can we even do partial configuration? Yes, we actually built it in that way in our chip. We could convert one lane into a CNN job, the other lane into CPU job. We could do that individually. And we could do half of CPU and half CN. So we build in that way. We try to demonstrate, but then turns out we have a hard time to find an application for those mode. So we didn't present in our paper, but we could do that. We could, depend on your usage, right? So you could, then maybe a case you need a small CPU, but then the rest you want to configure into the CNN operation. That's possible. So yeah, thank you.
Yeah, I think there's one audience want to ask. You can either unmute yourself or just input question in the chat.
Hello, Professor Gu. Many thanks for your presentation. So I start to follow your group's work in time domain computing because my own research is also like time domain in memory computing. I'm a PhD student from RWTH Aachen in Germany.
Okay.
I want to know, like, are your group still doing the research in time domain? Because so for the latest work in your group, I think it's from another student. Actually, like in this year's Accelerators, so we also present our time domain work, and I heard like one group member in your group, so he told me like you are still doing this research, but for me, I still didn't see any publications of that. So my question is like, because for analog computing and in memory and time domain computing, the noise is very important. So I want to know, like, how do you consider the noise difference between the analog computing and time domain computing, and how your group usually handle this kind of noise?
Yeah, we. By the way, thank you very much for reading our works. So yes, in the past few years, we did a lot of time domain computing work. The student who did that graduated, so we kind of have to restart the work and download the existing knowledge to a new student. So this is new student still working on that. We actually have a recent test chip using the time-based computing for robots application. But it turns out it's very, very complicated. We tried to put that chip into a real robot and took us a lot of time to get it to be working. So we're still measuring the chip in the lab. But I hope we can come up with a publication sometime this year. So we try to make it more useful. So that's why we're looking for real applications these days. So we're still doing that. But in terms of the time computing versus analog computing, essentially these two actually are similar, very similar, because even you talk about time domain computing, it's still a charge-based, and fundamentally still similar as analog computing. But time domain computing, in my own view, have benefit of the circuit are mainly digital. So in terms of robustness, it will be a little better than the analog computing. And the circuit by design, by itself, are mainly a digital circuit, which makes it more scalable and more in favor for advanced technology. So that's one benefit. Another one is for certain applications. For example, the dynamic programming chip we build, it's actually have major improvement. That's because the time pulse can be easily passed through a simple logic gates. So I would say if you want a very strong benefit, then you have to look for the algorithm that's suitable for this kind of application. But for general calculation, for example, CNN, there's already lots of work in different universities. Even I think this year, there's time domain CNN published in SSCC. So there's still under pretty heavy development now. Even the benefit, I think, is moderate. It's an interesting idea, and the concept could be lumped into the spiking-based operation. So really depends on how you use it. I think the application is the key. So in certain application, for example, that's why we are looking at the robot application. The sensor itself is in time domain. And then you do the time domain computing and then come back up with control or PWM control into the motor. Everything will be in time domain. That will save a huge effort in terms of data conversion. So that's where essentially near sensor computing, I think, is one of the potential for this kind of a computing method. We can have more discussion if you're interested in. We can have some other appointment with me. But yeah, thank you very much for raising an interesting question.
Yeah, maybe can send you an email after like this talk. Yeah, because like your group is a group like I always follow in time domain computing.
Great. Sure. I think you can. Yeah, we can set up a time. We can chat more. Thank you.
Okay, thank you.
I think another questions in the chat box. So what could be the future direction to extend this work? I think the word means the CNN neural CPU.
What I want to mention is we actually just designed a new version of this, but I don't want to talk too much because it's not been published. We actually extended this neural CPU into computing in memory, and we found actually a very major improvement in actually the CPU efficiency. We actually can achieve the best in class efficiency. So essentially, I think it's there are a lot of new architecture, but the new architecture could factor in the concept that we had in here, which would help us to extend. So that's one way of extending this work. Another one is we are thinking of a more neuron-based general computing platform where we could build a cluster of neurons or neuron kernels together to perform a sequence or cluster of general purpose programming job. Let's say you do certain amount of dedicated DSP processing in a loop. We could configure the neuron to support that kind of general kernel and using the existing neuron you had, right? So it can make it into a, again, group the neurons into a more general computing platform. That's another direction to go, extending this CNN-based operation into a more general signal processing application or also image processing. As far as you have a configuration, you have a support for different instructions, you can leverage this array of neurons to perform certain job much more efficiently compared to conventional architecture. So that's some of the future direction in this work.
Yeah, I remember this. Right now, there's one startup in the Silicon Valley. I think they're backed by the Qualcomm. Right now, they are doing kind of the base station chip can both support the edge AI and the 5G signal processing on the same chip. Yeah. Some similar concept you propose.
I think so. I think this has to be important for especially IoT application, where I was talking to Texas Instruments. They are putting things into their microcontroller of this kind of advanced computing support, and they're very limited by computing resource. And if you can do both in one core, then that's very, very important. So I think there's quite a bit of potential for this kind of architecture.
Other questions from the audience? So if no question from audience, actually I have one question. So in your first part of the talk, you merged the like CNN and the CPU together. So actually, so I think the backbone is kind of the neural work, right? So the neuron is kind of, and on the other side, like what right now ARM is doing, so they also want to merge them together using the kind of single platform, but their strategy seems like that the backbone is still kind of the ARM architecture, and then add the new AI specific instruction to the ISA. And so so how do you compare these two kind of different paths towards the same goal? What's your opinion about that?
I think our work fundamentally is much more finer granularity in terms of supporting the data path. So we get down into, you see the pipeline stages, where, so we break the pipeline stages and recover that from PE. Compared to the what you mentioned, the ARM approach, in my feeling, is more like a CGRA kind of approach, right? Configurable, reconfigurable logical array kind of approach. Each of them have a pretty strong core, and then you can build a larger data path or data pattern in that case. So these two are different. I would say ours is more at the micro architecture level, which go inside the core itself. The other approach will be at a higher level. It's easier to go with a higher level. Let's say you have a very nice reconfigured core and then connect them to deal with a larger job. It's harder to go with going down our path that is building, at pipeline stage level. I can't say who is more useful, but I think our job is giving this more fundamental understanding of what can be done. And really then it's come down to the cost, the benefit, and the application, whichever make more sense. So, but I'm glad to see that there are more people recognizing that the need to support both architectures and both jobs. And I think that it will inspire more interesting architecture being developed.
Thank you. And is there any other question from the audience? I have another follow-up question. So let me ask another. So when you merge these two together, so like, do you need to train your neural core to perform like the CPU? Or
for this work, no. It's I showed that our some very initial study, we try to train the neural network to do the CPU, but turns out that it's not very efficient in terms of hardware implementation. So we're no longer going that path, because it's the CPU job fairly easy to be done using a simple ASIC type of logic. So we all this is really more of a reconfigurable design rather than trained. Although the concept, I think, is more interesting going in that direction, but in terms of real implementation, the reconfigure design is more, I mean, probably at this moment more practical. But I like that direction actually, training neural network. Actually, the next, the second work, the differentiable neural computer, that's trained to do the job for cognitive task.
Okay. So in our just a conversation, you mentioned that like the CGI is kind of more high level optimization to achieve this reconfigurable.
Right. I think so.
Design,
yeah.
Right. So can your strategy and the CGI can be kind of complementary, used together?
I think there's a similarity of the idea in there, but if you look at each CGRA, going into it, it's more like a smaller CPU core inside it. So we actually break into the CPU core into the deeper of it and try to reconfigure it. If you can merge these two, then that means on top of our architecture, there will be multiple our systolic neural CPU together and doing even bigger job. I think that will be the extension of our work in that way. Yeah.
I see. Okay. Okay. So, any other questions from the audience? So, if no more questions, so let's thank our speaker, Professor Gu, again. So this is a really very interesting talk. I believe that it will inspire our audience a lot. Yeah. So thank you very much. And also, also thank all the attendees to join today's talk. And our next week's talk will be on the next Thursday. And look forward to see you guys again. Okay. Thank you very much. Thank you very much, Jie. So have a wonderful day. Thank you.
You too. Thank you. Bye-bye.
Bye. Keep in touch. Bye.
Yeah.